Good afternoon, students. Now we discuss about the lecture that is the monochromatic aberration. If the light is monochromatic, then the aberrations produced in an image are called monochromatic aberrations. Monochromatic aberrations are five types. So one is spherical aberration, second one coma, third one astigmatism, fourth one curvature, and fifth one distortion. The first three produce blurring image, means the image should not appear clear. The last two causes the dislocations within the image but no blur, means the image appear clear but some oscillations occurs in the shape of the image. Now discuss spherical aberration. So this is a large circular aperture of convex lens. So this is a monochromatic point source. So these rays are marginal rays, means the rays which moves near to the rim of the lens and away from the lens are called marginal rays. The paraxial rays, the rays which moves near to the principal axis and away from the rim of the lens, are called paraxial rays. So monochromatic point source is placed in front of the large circular aperture of convex lens on the principal axis. So here the marginal rays come to focus at point IM on the principal axis. Here the marginal image is formed, and the paraxial rays which are brought to focus at point IP. Here paraxial image is formed. So formed formed so all the rays which are brought to focus at different points between the IM and IP, so then the image should not appear clear, so due to the inability of convex lens. So so this is called spherical aberration. So the inability or failure of convex lens to form a point image of point object is called spherical aberration. The failure or inability of a lens to form a point image of point object called spherical aberration. So if the screen is placed at IM, so then the image appear on the screen should be disk. So the disk, the center of the disk appear bright and the outer edge of the disk appear blurred. If the screen is placed at IP, the same image obtained on the screen. So here also the disk, the center of the disk should appear bright. The blurred appear on the edge of the disk. If the screen is moved between IM and IP, so the size of the disk reduces to minimum, so called circle of least confusion. So the least confusion, so the radius of least circle of least confusion called lateral spherical aberration. So the distance between IM and IP are called longitudinal or axial spherical aberration. So the distance between marginal image to paraxial image is called longitudinal or axial spherical aberration. The spherical aberration for convex lens is positive because the image is formed opposite side of the object in case of convex lens. That's why spherical aberration is taken as positive. The spherical aberration in case of concave lens is negative because the image is formed on the same side of object of concave lens. So that's why the spherical aberration is negative for concave lenses. So now we discuss the minimization of spherical aberration. The first method, the spherical aberration can be minimized by using stops. The stops can be used to permit either paraxial rays or marginal rays of light. So here the stops used, here the stops stop the marginal rays and permit the paraxial rays which are meet at IP. Here the perfect image is formed. If the stop the paraxial rays, then the marginal rays are focused at IM. So and they produce the clear image. So the second method, that is the spherical aberration, may be minimized by using the suitable lenses in contact. Here, the convex lens and concave lens are combined together, so which are made with suitable material. So this combination may reduce the uh, spherical aberration. And the third one, the spherical aberration may be minimized by using a Crosshall lenses. So Crosshall lens is a double convex lens whose radii of curvature uh, are in the ratio, that is R1 is to R2, called Crosshall lens. The condition for a Crosshall lens is R1 by R2 is equal to 2 mu square minus mu minus 4 by mu into 2 mu plus 1, mu into 2 mu plus 1. So the refractive index of the cross lens, that is equal to 1.5. R1 by R2 is equal to minus 1 by 6. Okay. The ratio of the ratio of radii of cross lens is equal to 1.1 is to 6. So that lens should remove the spherical aberration. If the refractive index of a cross lens is 1.66, therefore the ratio of their radii is equal to 1 minus 1 by 6.5. If mu is equal to 1.686, so this value substitute here, so we will get these values. So R1 by R2 is equal to 0. So these all conditions obey the double convex lens. So those are called cross lenses. So cross lens may be reduce the spherical aberrations. So like this cross lens, so this is the cross lens. So this surface is more surface area, this is more surface, this is small surface. This radii of curvature is less, this is more. So what is radius of curvature? The distance between the center of the lens to the optic center of the lens is called radius of curvature. And the fifth one, the fourth one, the spherical aberration may be minimized by using two plano-convex lenses separated by a distance. So that is equal. For example, here the two plano-convex lenses, their focal lengths f1 and f2, and separated by a distance d. So this separation should be equal to difference of their focal lengths. So if this condition is satisfied, then this system reduces the spherical aberration. So and fifth one, the spherical aberration may be minimized by using a planitic surface. So planitic surface which form a point image of a point object. So this surface may be reduce the spherical aberration. So thank you. Now see the answer from starting to